Alcohols undergo dehydration in the presence of concentrated phosphoric acid via a carbocation intermediate to form alkenes. So this is the elimination from an alcohol mechanism. Complete the mechanism for the conversion of 2-methyl-cyclohexanol into 1-methyl-cyclohexane via a carbocation D by drawing the structure of the missing intermediate and all necessary Cayley arrows. So they've helped us out here because they've put a lone pair on this oxygen and they've shown us that proton from the phosphoric acid. So that's our first mark. Let's draw what that leads us to. So we've made, haven't done anything to this CH3, we haven't done anything to this H. What we've done is added an extra hydrogen onto this oxygen. As a result, this oxygen's become positive. So that's our intermediate. We would then need to lose this water molecule. So we would do a curly arrow from the bond, put the electrons on the oxygen and lose that positive charge on the oxygen. So there'd be some water sort of floating around here. As a result of the carbon giving up its share of the pair of electrons in the bond, it now becomes positive. And in order to end up with a double bond, if we can see that the double bond has ended up here, then this is where we want it to end up. Then the hydrogen from the next door neighbour carbon that is to that side is the one that must give its electrons to make the double bond, and we lose a H+, and we've catalysed our reaction because H+ went in at the beginning and came back out at the end. It says, what else could we have made? Well, if you look at where you took the hydrogen from, you took it from the top carbon. If we'd have gone the other side, this side down here, then our double bond would have ended up in a different place. So we don't need to show the hydrogens on a skeletal formula. They did that up there to help you with the mechanism. If we put the double bond where the green highlighting was, then the double bond ends up here, and that would be a different cyclic alkene. It then says carbocation D, so it's drawn it for us again, can undergo a type of rearrangement to form carbocation E. Notice that the plus has moved from here to here, and the H has moved from, or a hydrogen has moved. Use your knowledge of carbocations and so we're talking about carbocation stability to say why that would happen. So if we look at the carbocation E, why would that form? Well, if we look, this carbocation here, it's got 1, 2, 3 carbons directly attached. That makes that a tertiary carbocation intermediate. So carbocation E is tertiary, whereas D is, and if we look at D, it's only got 1, 2 carbons attached, so secondary. And these carbons, these alkyl groups that are attached, make that carbocation more stable. So it would happen because it's more stable to be E than it is to be D. It wants to be more stable, lower in energy, so it rearranges to be carbocation E. As a result of that rearrangement, there's now a third alkene that could form. Now the plus is now, if we go up, the plus is now here. Okay, so double bonds could form any carbon attached to this, so either here, here, or here. Now, the second two that I drew are actually the structure we already had as the product in the very first part of the question. And so we want the extra one, the top, where the double bond forms between the carbon of the methyl group and the ring.